seniors for their part. I believe it is too long for seniors to go to sleep. So I'm going to get the homework today. I
Okay.
just wanted to leave.
Yeah, that's fine. First, I'm going to get into some of those details.
Yeah, I just wanted to let you know.
Oh dear. All right. How's everyone doing today?
Pretty good.
Okay. Good weekends, I hope.
Yes,
All right. Excuse me. All right. So, this week we're going to be continuing with chapter 1. My hope is to finish up chapter 1 pretty soon, maybe begin chapter 2 sometime this week. We will be having labs starting this week, so do keep that in mind. This first week's lab is just going to be a quick sort of introductory lab, sort of an algebra review type of assignment, and covering some of the material we talked about so far. It's one of its main focuses is to get you used to coming to lab at 1:30. So this week, whatever day of the week your lab assignment is, do come to this room at 1:30 for your lab. If you're not able to make it in person, please let me know, email, and I'll work out what you'll be doing instead. Now, we're also going to talk a little bit about sampling today, making sure everyone can start accessing it, talking about the first homework assignment. Before we get started, before you get too far in, does anyone have any questions about anything?
When would our first quiz or exam be like?
So there's going to be about one homework and one quiz online every week. So, you know what that means?
So all on sapling?
Yes, the homeworks and quizzes and possibly tests are all going to be via sapling.
Is that like a different version of Brightspace?
So-
Use that instead of Brightspace?
Brightspace is the school's tool for course information, but it doesn't have any built-in like virtual homework assignments that I'm aware of. A tool to actually let you do an automated assignment. Sapling's benefit is it lets you construct homework assignments that you can do in browser. Gives you the question, you can submit your answer, and it'll tell you then and there whether or not your answer is correct, and then you can try again if you didn't get it right.
Is there an app for it, or is it just a website?
I don't know if they have an app version. I've only ever accessed it through browser. But I have used it through phone browser at the very least. Not sure on an app, but it's useful as an online homework tool because this is the teacher view. Oh no, you can't see the teacher view. Hang on. So when you get into Sapling, and I'll show sort of a couple of other pages to give some more insight as to how to do that. The assignments will be listed at the top of your page. This is the first homework, and this is the first quiz. We'll have about one of each for each chapter, and we'll have about one chapter every week or two. So there'll be about 10 homeworks and 10 quizzes spread out about a little over 10 to 12 weeks. So usually about one per week. And each homework will be inclusive of everything we do for the unit it is attached to. So I encourage you, once you gain access, to go ahead and look at the Chapter 1 homework, but it contains everything for all of Chapter 1, which we have not technically finished yet. So there's things in there you might not be able to work just yet, and that's fine, that's by design. I want you to read it and start working on what you do know, and what you don't know is stuff we're going to cover in class. And then when we finish Chapter 1, I'll make it due after we're done with the notes and lecture. Presently, I've got both of these due for September the 1st. I'm going to scroll down here to my calendar just to show that September 1st is next Tuesday. And what I do with with pretty much every assignment is I make it due midnight on that day, or just before midnight, 11:59, so that my goal is if we finish Chapter 1 this week, Then you have the weekend to do whatever you need to with it. And then we'll meet in class on that Tuesday. So say we finish chapter 1 these 2 days, then you have the weekend to work on your homework, and you can come in on Tuesday and lecture to ask me any questions you need, and then we do that night. It's my usual MO when it comes to these. The homeworks, I want you to look at those as soon as possible so that you can get into them and start them, so you can go back to them and take as many tries as you need. The quiz is the last thing you do. The quiz is what you do after you're done with the homework, because you only get one. You only have 1 hour to submit your 2 best answers for everything. Okay? So the homework is sort of the slow practice approach, and the quiz is sort of the small, very low stakes live fire exercise. Now, I've seen some people already begin accessing Sapling and beginning the homework, which is great, but I've also had lots of people with issues sort of getting their account set up. So what I'm going to do now is, I'm just going to sort of show you the account creation process and what your screens should look like as you're getting into the tool. So, there's a couple different links I've posted to the Sapling service. It is done by a company called Macmillian, so you can get there through the Macmillian Learning website. And Sapling is just one of the services they provide. This is what we're having you pay for instead of a physical textbook, so we can do all of our homework online. If you make it to this page, you just click on sign in/register. Make sure you're signing in as a student. If you click on that, if you already have your account, you can sign in. If you don't, you create one. You put in all of your vital information, name, last name, email address. List your school email address for this, but this is your password for the account, not your password for your school address. If you make all your passwords separate, keep that in mind. Also, primary school institution. Previously, the tool has had issues recognizing Presbyterian College, but it seems like that is now an official autofill option. So if you're making your account for the first time, you should be able to select Presbyterian College. If you've already made it through this window and that option didn't exist yet, and that causes trouble later on, please let me know, and I'll try to get through the instructor portal, try to get Macmillian to work on that. Then after you list your college, you just list your security questions. You don't need emails from them, but you do need to agree to terms and services, and then you create your account. It'll then say that they've sent an email to you asking you to verify your account. It might take you like 30 minutes to an hour to actually get that email. It might show up immediately. It might not. When it shows up, you just verify your account through that email, and then what you will see will look something like this. No, it'll look something like this. If you told them that you attend Presbyterian College, it will automatically try to fill you into one of the courses at Presbyterian College, of which there is actually only one. This is the only class that is currently using Sapling this semester. So if you just go through these drop-down boxes, you'll find the only class listed for this semester. Again, BC, Phys1000, fall 2020, my last name, and this is the point where you would submit the entrance fee for the access to the tool. You only need to pay this once, and this is instead of a textbook.
How are you?
Oh no? The textbook is an optional supplement. If you don't want it, you can please resell it. Return it. It is optional. It is good if you want it. It is good if you want a book.
I don't want to do it.
Okay, in that case, by all means, if you need to, return it or resell it. I lost count of how many math and physics books I've accumulated over the years. They're currently taking up space on my office bookshelves. And again, if you were able to list Presbyterian College in the account making process, that should all just be right there for you. If you already made your account, but when you make it to this screen, it doesn't automatically do this, please let me know, and I'll try to see if I'll try to get onto the administrator of the site to see what they can do about that. Yes.
That happened to me. It just like gave me an account. It didn't let me choose the option for your class.
Did you didn't give them money yet, right?
No, I looked up like you could buy the homework, just like the homework thing for $42, but I don't know if it would work.
Okay.
I was.
Maybe you can view profile, edit profile. You might be able to, okay, you might be able to go in and change.
I just did that. It's still the same thing.
Well, that's frustrating. This is just my backup account, so I can log in as a student.
Just make a new account.
Possibly. You haven't given them any money yet. I think you can make more than one account per email address, I hope. Again, if it's giving you more trouble than that, I will nag them from my end. I just need, if you can send me an email with your name and login.
Gotcha.
At least your name and your info, I don't want your password. Okay. But once you enroll in the course, you should be able to make it to the homepage with the homeworks on it. Any other questions about this right now? Okay, so if anyone as an individual has any issues with this, let me know immediately. Please send me an email. That way I have your name and your complaint on file, and I can send it to Macmillan. I've had to nag them several times in the past. They know me, and they're actually pretty quick about it, so I will try to get everything, any issues sorted as they arise. And I'm all ready to proceed. Okay, so the homework will be done through the sapling site. People have also asked where to find video lectures and notes. That is going to be through Brightspace. Only this class is using sapling. This is this class's homework tool, but the whole school uses Brightspace as a sort of database. So when you log into your Brightspace page, it'll show you all the courses you're registered for. Click on this course. And then it'll show all the chapters that we have here so far. I have more things viewable because I'm an instructor. Your account should only have these first two things at the moment. If you go into chapter 1, it'll list everything we have for chapter 1 so far. This is all of our links to the lectures that I've already recorded. I'll be adding more. I'm hopefully going to be able to just stream the lectures live and then post the recordings, and I'll put all that information here. Every single chapter has this tab right here where you can click on it, you can just get info on the chapter, and then there's documents uploaded under it that will be like notes and extra assignments. So this is where you can find all the slideshows. I do edit the slideshows this is my original draft, and I edit it, add examples as we go through it, and so I'll try to upload the final version as well at the end of the chapter. But that is where you can find all of that information. Other things will be available there too. So again, the difference is we're using Sapling for homework. The whole school uses this as a database. And you're automatically signed up with a Brightspace account through the school. Okay. Now, all right. So last week we left off talking about one-dimensional motion. We specifically did some examples related to displacement and velocity. Does anyone have any questions or issues or needs before we resume that? Okay, so we're talking about one-dimensional motion. Again, if something is moving one-dimensionally, it is bound to a single axis. We live in 3D space. We can go either in the x-axis or the y-axis or the z-axis, but we're just looking at x for right now. Displacement in a single axis is just going to be the physical length between 2 points. You can measure the physical length between the 2 ends of this meter stick. Velocity, meanwhile, is the change in displacement the change in displacement over time. In order to have velocity, also in order to have speed, you have to be moving some distance through space over a period of time. I talked about acceleration in a second, but I'm actually going to tab to the next slide real quick, and we're going to begin just with a displacement velocity review question, just to start with. So, quick piece of practice. You drive for 30 minutes on the interstate, where the speed limit is 70 miles per hour. So, the first things we are told, velocity 1. This 1 is sort of a subscript. I'm using that to say this is the first velocity that we are given. Velocity 1 is 70 miles per hour. I am speed improving. There we go. And we drive at this particular speed for 30 minutes. So this is our first time that we are told. The limit then drops to 60 miles per hour, and we drive at that speed for 40 minutes. So we are given a new velocity and a new time. Lastly, you're asked, what is your total displacement for this whole trip? Now, the way I've written total displacement is as sigma d. This is the Greek letter sigma. If you've been on campus very long, you've definitely seen it and heard it. Does anyone know what this letter is used for in terms of math?
Summation.
Say again?
Summation.
Summation, very good. Sigma anything means, I'm spelling it out, sum of. Sigma d in this case is going to be the sum of all of the distances that we have traveled. Sigma anything means you take all of that thing and add them together. In the next units, we're going to be talking about the total amount of force on an object. So sigma force, sum of the forces, you'd add up every force acting on an object. Like if there's 30 people trying to push something, and they all exert 10 newtons, you add up all their forces together to find the total force. So this letter will mean SUM, sum of, you're going to add all of that thing together. So we're going to want to find the total displacement that this car has driven over both of these intervals of time. There's 2 separate time intervals here. During each one, we'll have driven a different displacement. We want to know what the total between the 2 is. So, with the information we have, where should we begin? All right. Converting minutes to hours is a pretty good starting point because this is miles per hour and these are in units of minutes. Those aren't going to be compatible if we have to start multiplying. So preemptively converting is a good move. So how many hours is 30 minutes? All right, it's half an hour. So I'm going to write that out as a decimal. 0.5 hours. How many hours is 40 minutes going to be? 2/3 of an hour. Very good. I'm going to write that out as a decimal again. I'm going to round that to 0.67 hours. So we converted all of our times into hours, which is the same unit of time as written in our velocities. What can we do with those pieces of information now?
Use a formula.
Which formula?
Velocity changing equals changing d over changing time.
Very good. So again, we're just practicing our standard order of operations here. If this is what we know, and this is what we want. We look at our formula sheet, determine what formula contains all of these variables together. This is our one formula so far. It has V, D, and T in it. We can use this to find our displacement. Now, I wrote these subscripts up here, V sub 1, V sub 2. The subscripts would help differentiate between the two different phases of this question. Because there's, we move at this velocity for this amount of time, we need to keep that separate from this velocity at this amount of time. You don't want to accidentally multiply this velocity by a time where we were not traveling at that velocity. So we're going to need to do this formula twice. Once for our subscript 1 variables, and a second time for our subscript 2 variables. For the first set, we have a velocity of 70, and that's going to be equal to delta D1 over time, so that's 0.5 hours. And what's that going to give us for the displacement in phase 1? Very good. So algebraically, we're going to want to multiply both sides by 0.5. That's going to cancel the 0.5s over here and bring it over to the other side. I should actually write that whole step out so people can visualize it. So I've done the same thing to both sides. That means it's algebraically legal. That will let us cancel these 0.5s. And it's going to leave us with delta D1 equals 70 times 1/2. And that is, in fact, going to leave us with D equals 35 miles. So that is how far you went before you changed speed. Before that, just in that first jump, before the speed change, you traveled 35 miles. Then for the second part, the 2s, we traveled at 60 miles per hour for 0.67 hours. We went ahead and converted to hours. We're just going to algebraically do the same thing. We're going to multiply both sides by 0.67. That's going to simplify to 60 times 0.67. And so what is delta D2 going to be? 40.2. Very good. I'm just going to round that to 40. But yes, depending on how your calculator rounded it, that is an acceptable answer. I'm rounding it to 40 because 40 minutes is 2/3 of an hour and 2/3 of 60 is 40. I know that error came from the rounding of the calculator when we found this, but if you still wrote down 40.2, 40.02, I would accept that as an answer. So, in phase 2, we traveled 40 miles. Notice even though we were moving slower, we were moving at a lower speed for more time, and we still went farther in this phase than in this phase. Kind of a tortoise and the hare situation. So, we know what each phase was, and now to find how far we went over the entire trip, we're just going to want to find the sum. We just want to add them together. So what is our final answer for sigma displacement? 75 tons. Very good. And that is how to do physics questions. This is all, like, concept-wise, this is all review, just dusting off the cobwebs and reviewing our methodology. Okay. Any questions so far? So, in this actual question here, something happened that we sort of glossed over. In the first part, we're moving at 70 miles per hour. We're assuming that that's a constant speed. The entire time we're moving at 70 miles per hour, and in general, this formula here assumes you are moving at a constant velocity. You need to be moving at a constant velocity for this formula to work right. If something is moving at a constant velocity, its velocity does not change. It's moving at the same speed in the same direction indefinitely until something happens. So to begin with, we're moving constantly at 70, but then in the second half, we drop to 60. Now, from that point onwards, we're moving at constant speed again, but something had to happen between here and here. If we were looking at this realistically, say you were actually the person at the wheel, what had to happen between here and here? Yeah.
Slow down, decelerated.
Okay, good. You slowed down, you decelerated. Deceleration is a good word. If you haven't seen that word spelled, actually, that has 2 L's in it. Now, in the English language, we tend to use the word deceleration specifically for slowing down. Does it have 2 L's in it? I'm making a mistake.
Yes,
Pretty sure only has one.
Okay. It does only have one. I am a physicist, I am not an Englishist. That's just 1 L. Deceleration. In the common English vernacular, we tend to use this exclusively to referring to slowing down. If you were, say, speeding up at the wheel, what would you say instead?
acceleration.
Very good. Acceleration. Same word, just replace the prefix. So we tend to use this word in most common parlance English exclusively to mean going faster. But the physics definition of acceleration, which is what we care about for this class, the physics definition of acceleration is a measure of the rate of change of velocity. If velocity changes, you are accelerating. The definition of acceleration is just a change in velocity. When you get in your car to start driving, your car has to accelerate from an initial velocity of 0 up to some other velocity so that you can go somewhere. Because if you stayed at 0, you're not going anywhere. So to use your car, is everyone okay if I erase this? To use your car, assuming you had it parked and turned off, for it to be of any use to you, your car has to undergo an acceleration. You get in, turn it on. Today you're all drawing a poorly drawn purple sedan. When you get in and it is parked, what I'm writing here is VI for velocity initial. So whenever I use a subscript I, that's going to mean initial. The initial velocity before you start your car up is what? What speed is your car moving when it's parked?
0.
Very good. 0, I'm just going to use meters per second. I also sometimes write my zeros like this, differentiate them from my O's. So this is 0, not to be confused with the Greek letter theta, which will also come up. So that's 0. The initial speed of your car when you first get in it is here. What do you then do to make the car do its job?
Step on the gas.
Step on the gas. What is something else we tend to refer to the gas pedal as? The accelerator. It is the thing you do to make your car accelerate. So let's just say you accelerate up to some final speed of 30 meters per second. That might feel slow, but keep in mind that's meters in a second. not feet, not miles per hour. This is meters per second. This is actually very fast. That's basically covering a football field in a second. So this is a high top speed, don't speed. So you have to go from 0 to 30, and does that happen instantaneously? No. When you are driving, you put your pedal on the gas, you watch the needle slowly go up from 0 to 30. Again, I know your cars aren't in meters per second, but you need to get you used to using this unit. You slowly watch it rise from 0 to whatever speed you're going to, and you can count how many seconds that takes. It takes some amount of time. A lot of car commercials will talk about how long it takes the car to go from 0 miles per hour to 60 miles per hour. A lot of manufacturers and car testers really do care about the 0 to 60 time. Let's just say that in your car, it took you 5 seconds this morning, just gunning the gas, to go from 0 to 30 meters per second. So, in this amount of time, your car's velocity changed from here to here. By definition, that is an acceleration. You sped up from here to here in this amount of time. That is everything we need to calculate the acceleration of your car. So, the formula for acceleration is written right over here. I'm going to write it on the board in a second. Acceleration, the variable we use for that is a lowercase a. This is lowercase a. Uppercase a is usually reserved for area. Lowercase a is acceleration. So acceleration is equal to change in velocity over change in time. If you remember from a second ago, displacement is velocity is change in displacement over time. To have a velocity, you have to be moving. In order to have acceleration, you have to be changing velocity over time. Now, delta represents the change in, and as a general rule, I'm going to sort of make this a little bit bigger. I'm going to expand this out one step. Delta anything means final minus initial. In order to find the change in something, you need to look at where it wound up and compare it to where it started. So delta anything is final minus initial. For this specific question, delta velocity, change in velocity, is final velocity minus initial velocity. So, for the example of your car right here, with these numbers up on the board, if you wanted to find the acceleration of your car, you get up to 30 from 0, and that took you 5 seconds. So what would the acceleration of your car be?
6 meters per second squared.
6 meters per second squared. Very good. That squared is important. So 30 minus 0 is 30. 30 divided by 5 is 6. So that's where the 6 came from. But where did that squared on the meters per second come from?
30 meters per second being divided by 5 seconds.
Very good. This is velocity over time. Velocity is measured in meters per second, and then the time that we would plug in for t is also seconds. Now, this is meters per second per second. That doesn't cancel seconds out. If we were to sort of expand this to the next step, we're dividing meters per second by seconds. We're not multiplying it by seconds, we're dividing it by seconds, which would be the same thing as writing it like this. So meters over seconds times 1 over seconds. M times 1 is m, seconds times seconds is seconds squared. So the unit of acceleration, with my red marker, the unit of acceleration, whenever we talk about an acceleration, it'll be measured in units of meters per second squared. It's very important to differentiate that unit. I myself have made mistakes where I'm doing a problem I don't write the unit down right. And then when I look back at that part of the work, I see, 6 meters per second, and I think, oh, it's a velocity. I'm just gonna plug it into velocity down here, and then everything I do is wrong. So, the squared is very important. It will help you, it will help me. Now, like I was saying, we tend to use the word acceleration to refer almost exclusively to speeding up in common English. But the physics definition doesn't care if you are speeding up or slowing down. Either one, where in English we would call slowing down a deceleration, in physics we tend to just use the word acceleration to refer to both. So, if I could change the example on the board for a second, you don't need to erase what's in your notes, I'm just modifying what's on the board because it's easier to change it than to rewrite it. Let's say that you were driving at 30, and then you hit the brakes to slow down. So I just changed which one's the initial and which one's the final. This is a second example, separate example, don't erase anything. Let's say you were moving at 30 and then you hit the brakes to slow to a stop. That's going to change which one is the initial and which one is the final. That's going to mean we have to switch these. So that's final minus initial, 0 minus 30. That puts a negative sign on our answer. This is still an acceleration, it's just in the negative direction. In the negative direction. I realize my negative sign is selected. We still call it an acceleration because even though your velocity is becoming smaller, it is actually becoming bigger if you consider bigger to be in the negative direction. It's kind of just about your perspective. If instead of just hitting the brakes and stopping here, you slammed it into reverse, if you pressing the gas in reverse, you would eventually go faster backwards. So slowing down is still accelerating because your velocity is changing and your velocity is becoming bigger in the opposite direction. Okay? I've been talking for a while and might not have phrased that as best as I could. So, and I'm thirsty. So if anyone needs a quick minute for water or bathroom or emails, that's fine. We're going to come back in a second and talk about how to sort of apply the directionality of these units so far. And then we're going to talk more about acceleration. before we resume.
How would we convert the meters per second squared to like other things, like kilometers or hours?
Okay, good question. Good question. It kind of depends on what part of it you're converting. So, say we just had 10 meters per second squared, and we wanted to make it kilometers per second squared. That's pretty easy. We just need to turn the meters into kilometers. So there's 1,000 meters in every kilometer, because kilo is a factor of 1,000. If we orient it like this, that'll cancel meters. And if all you wanted to do was change the meters, this is all you would need to do. This, just dividing by 1,000, would give you kilometers per second squared. If you wanted to convert it to like meters per hour squared, that sort of adds an extra step. So say, well, okay, how many seconds are in an hour off the top of your head?
A lot.
It is a lot. So 60 seconds in a minute, 60 minutes in an hour, it's going to be 60 times 60.
3,600.
Yes, so 60 times 60 is 3,600. There's 3,600 seconds in an hour. I have that number easily accessible in my brain because I use it all the time. If you're better with 60 times 60, that's fine. I know this because of the things I do for a living. So there's this many seconds in 1 hour. If we orient it like this, that'll cancel one of the seconds, but this was seconds squared, so we have to do it again. So if you're converting the time part of it, keep in mind that's squared, you'd have to do the conversion twice. It works the same way as anything else we've done. That's the one thing to be aware of when converting anything with a squared or a third in it. Okay, so acceleration is acceleration, whether or not you are speeding up or slowing down. Largely, that is the case because acceleration is considered to be something called a vector. Every math problem you've ever done, any physics problem you've ever done, anything you've ever measured, all of those numbers are either scalars or vectors. And these are just two fancy words that tell you whether or not the thing you measured has a direction attached to it. If something you measured is a scalar, it doesn't have a direction involved. Things that are always scalars, some measurements you've taken that are always scalars, are time. You can tell me 5 hours have passed, but you can't have 5 hours north. You can't tell me what direction time is in because it's just time. The amount of time, you can tell me the magnitude of the passage of time, but you cannot tell me the direction of time passing because there's only really one direction. There's no point listing it. I keep misplacing my one eraser, and it winds up being where I wanted it to be anyway. So I'm just going to define a few more things on the board as we go through what a scalar versus a vector is. Magnitude is a fancy way of saying how big the number is. In order for you to have a scalar quantity, it needs a magnitude. It needs to actually be a number. To have a scalar measurement, you need to be able to actually measure a number. As long as you can measure a number of something and there's no direction attached, it's a scalar. Your mass is a scalar. It's just a number that tells you how much matter is inside your body, but you can't have 5 kilograms east. It's just 5 kilograms. Your volume is a scalar. You could occupy 3 cubic meters of space, but you can't do that up. You just do it directionlessly. So, scalars only have a magnitude and no direction. A scalar is just a number with no direction attached. Meanwhile, a vector has magnitude and direction. In order to have a vector, you have to be doing something in a direction. Your car's speedometer tells you how fast you're going. But if you only look at the speedometer by itself, say you're going 70 miles per hour, that is only telling you your speed. It's only telling you the magnitude of how fast you're going. But if your car has like the little electronic compass up in your rear view, it tells you 70 miles per hour north, then you know your vector velocity. So, scalar, just a number with no direction involved. Vectors is a number with a direction stuck to it. Vectors you can also usually draw as an arrow. You can physically draw, you know, I'm going this fast this way. I have displaced this amount of space in this direction. Both of the things, actually all three of the things, if we include acceleration that we've talked about so far, are vectors. You have to displace in a direction. I was here, I'm now here, this is the direction I displaced in. And the magnitude is just how far I went. Velocity is specifically how fast you're moving in a direction. It's important to differentiate between speed, which is just the magnitude of your movement, to velocity, which is magnitude and direction. The reason we're going to use velocity in this class is even when you're just looking at one-dimensional motion, if this is the one axis we can move on, I can move forwards or backwards in this one axis. So your direction is still important even if there's only two ways you can go. Man, this thing contains a lot of my hot air. How are you doing so far? Okay. So, everything we've talked about so far is a vector. When I mention new variables, when I give you new variables, I will tell you whether or not they are vectors. So you can add into your notes for all three of these things, vector. They need a direction. They are best when written with a direction. So with the acceleration of the car we were just looking at, positive means you're accelerating forwards, negative just means you're accelerating backwards. You're becoming faster in the negative direction. And my cable just disconnected. But that's fine, because I actually wanted to show you something off of the screen. I have not gotten the speakers. I don't even know if this projection system has speakers, frankly. So I'm going to show you something just on my computer because then the actual sound will play correctly. Even if you've never done work with math vectors before, I guarantee it's not an entirely foreign concept to all of you because, for better or worse, you've probably all seen this movie. Not the Bee movie. So, even if only as a joke, you've heard of this before. Sorry for the speakers, there's none in the still. So, displacement, velocity, acceleration, all vectors worth writing into your notes. They are best when written with a direction. So far, that direction's only really going to be forwards or backwards, positive or negative, but that's why including positive versus negative signs is important, which will further be elaborated on in our next example. I can find it. There we go. So, we're going to begin looking at this next example. We're going to begin looking at it. We're only going to do the first part of it real quick. We'll get to the second one in a second. The second phase of this one, because that requires a different formula. Right now, we're just going to focus on the first part. So, you drop a stationary object that begins accelerating down at the acceleration of gravity, which is 9.8 meters per second squared, downwards. So, before we have to do much with the question itself, just to explain, gravity on Earth's surface acts as an accelerant. It causes objects to begin accelerating downwards. So, again, if you were in Newton's shoes, this is a terrible representation of an apple, but if this was the apple for some reason, what velocity does it start at?
0.
0. What velocity does it end at? It ends at some velocity that isn't 0. It is now moving downwards, therefore it had to accelerate. So gravity causes things to accelerate towards the center of the Earth. Gravity acts as an acceleration. It causes things to accelerate on Earth's surface. Now, I imagine most of you have done this. I know I certainly have, and nearly broke my feet doing it. Swing sets when you're young. You ever play the game where you try to get up as high as you can and then jump off?
I try to do a flip like.
You're a braver kid than I. Please do not injure your neck, or your spine, or your tailbone, or your head. So, why is it more fun to jump off when you reach higher up?
You go faster now.
Okay, so I'm going to draw two comparative lines here. Let's say you jump off at this height versus jumping off at this height. So this is like, you just hop off after using it, no issue, your mom wouldn't yell at you seeing you do this. But if you jump off all the way up here, what's going to be the difference when you land between these two?
Your momentum's going to take you down faster.
Okay, we're going to get into momentum in a few weeks. It's a good word. For right now, I'm just going to you're right. You are right. I'm not going to take away your correct answer there. I'm just going to simplify a little bit and rewind to just velocity and acceleration. But very good. Excellent. So, now, the way that gravity on Earth works, it doesn't matter what height you're at, the acceleration is the same. Gravity pulls down on you at the same rate as long as you're still on Earth's surface or near Earth's surface. So, regardless of where you start, you're going to accelerate down at the established Earth gravity rate of negative 9.8 meters per second squared. The negative just means down. So regardless of where you start at, this is the rate at which you're going to accelerate. But if you start up here, you're going to spend more time in the air. That's more time to accelerate up to a higher speed, and then you hit the ground. So, yes, definitely more fun. But when you hit the ground at a higher speed, it's going to hurt more. So just keep that in mind. Don't launch yourself high enough to break your ankles. But, again, this is sort of evidence that Earth's gravity acts as a uniform accelerating force on things, and the amount of time in the air determines what speed you're going to hit the ground at. Usually the harder something hits the ground, the louder the noise it'll make. So just as a quick proof of that, not very loud if I just drop it from here. Doesn't hit very fast, but more noise means there was more energy in the collision and it hit faster. So more time in the air means more, it has time to accelerate to a higher velocity, which is what we're going to prove here now. So, let's reread the question. You drop a stationary object that begins accelerating down at the acceleration due to gravity, 9.8 meters per second squared. So let's just say you're dropping a baseball, a poorly drawn purple baseball. Just reading the question, even though it doesn't list the number, what do we know our initial velocity is going to be?
0.
0. It says that we begin as a stationary object. So V1 is 0 meters per second. We are told our acceleration, so our acceleration is going to be negative 9.8 meters per second squared. I have a hard time putting the squared on the S in Microsoft Excel, in PowerPoint. This little sort of upside down V here represents mathematically to the power of. So this is S to the power of 2 seconds squared. It's a useful symbol to recognize because odds are you're going to need to use that symbol when you use your calculator. For example, say a question told you to solve 9 to the power of 15. Your calculator may have a squared button, but it doesn't have a to the 15th button. So on my calculator, what I would do there is I hit 9, and then I hit this little symbol. I've heard it called caret. I've heard it called hat. I might use both of those interchangeably. It's the upside down, upward pointing V, the caret button, the hat button, what have you. Press that, and then hit 15, and that'll be at 9 to the power of 15. You press enter, and you get your really big answer. So when you see that symbol, that's what it means. It's just to the power of, if you haven't used that before. So we've got our acceleration of negative 9.8 meters per second squared. Negative is important. It means down. And we are told we are in the air for 3 seconds. And we are asked to find final velocity. We read the question, we've listed what we know and what we want. What do we do next? All right. What formula do you think is our best guess for this one? We've only really covered 2.
With velocity, equals acceleration times time.
Okay, good. That is the correct formula. You took what the established one is and you algebraed it a little bit, which is good, which is fine. I'm going to show them how to get there. So, the formula, as you would probably find written on your formula sheet, looks something like this. The definition of acceleration is change in velocity over change in time. Now, we can perform algebra upon this. If we multiply both sides by delta t, we can change this slightly. We get delta t times a equals delta v. So we can find velocity from time and acceleration. Something important to recognize from before, delta v represents v final minus v initial. I'm just going to write that out in full so that you have it in your notes and so that you're used to it. Because technically we're here to find Vf, not delta v. So this is where we started. We performed a little bit of algebra and expanded delta v to get to here. We know t, we know a, we want Vf, we know Vi, we're good to go. Just start plugging things in. We've got 3 times a negative 9.8 is equal to Vf minus 0. So ultimately our answer is just going to be VF times, 3 times negative 9.8. Someone use their calculator real quick and tell me what that is. Good. Very good. We're back to meters per second. We're solving for velocity here. We multiplied acceleration by time, we canceled the squared, we're just left with meters per second. And that would be our velocity after 3 seconds. I feel a sneeze coming on, but as soon as you prepare for it, it doesn't happen. So I'll just keep this in case it shows up. Any questions about this example? Okay. Now, hypothetically, if I dropped it from closer to the ground and it only had 2 seconds to fall, we'd be multiplying this by 2 and we'd get a smaller answer. You don't have as much time, therefore you do not accelerate up to as high a speed. Meanwhile, if I held it higher up, you'd have more time in the air, T would be bigger, we'd end up at a bigger final velocity. So this would be the speed at which you hit the ground. If you start closer to the ground, you won't be at as high a speed as when you start from higher up. Your starting height determines how long you're in the air, and that determines how fast you're going to hit the ground. How fast you will be when you hit the ground. Cool. Direction is also important. This tells us down, because on Earth objects don't tend to fall up. Don't tend to, at least. Okay. So far we've been using mostly just 2 different formulas. You have the formula that defines velocity and the formula that defines acceleration. I'm going to give you 2 new ones so that you have them when you start looking at your homework. The 2 that we have looked at are sort of part of a quartet that this physics department really likes. These 4 form the backbone of standard motion when you're just examining motion in 1 or 2 dimensions. These formulas are the backbone of all of that type of motion. And so when I was a student here, my professor has taught me these 4 equations go together, they are a team. And for as long as I have been associated with this school, the school has been calling them the Fantastic Four for that reason. Although when I was here in like 2010, they were using artwork from the Sony mid-2000s movies. When I started working here again, one of my previous professors had put up artwork of the more recent Fantastic Four movie, the one we don't like to talk about. I have since replaced it with artwork from one of the better, more recent comics. So do go ahead and write these down. These are also on the formula sheet available on the Brightspace page. We've already talked about the first 2. So you already know half of the Fantastic Four. The only new things here are these 2 formulas. Now this formula here, the 4th one, is the one we use the least of. It does come up, but we use it the least. The one I want to focus on right now, the one that's more useful more of the time, is number 3. So, for most of our questions, like the example we started with, I'm just putting it up to show you guys, don't erase anything. In the 2 separate parts of this question, we were assuming the object was moving at constant velocity and not accelerating, except for the little blip in the middle that we didn't do any math for, We're assuming no acceleration, just moving at constant velocity. But when you get in your car and you hit the accelerator and you speed up, do you stay in one place until the speedometer reads the speed you want it to? No. As you accelerate, you're already moving at some velocity. You're just moving at a slower one than you'd like to be. And you keep moving as you keep accelerating. When your velocity changes, you're still moving, usually. This formula, again, I tried to warn you, sometimes we use D, sometimes we use X. But this X represents, all of these X's here represent displacement. Again, disclaimer, X and D are interchangeable, my apologies. This formula here, I'm going to put the board up so I can put the board next to it. This formula is for displacement with or without constant acceleration. Hang on, let me rewrite that. This formula right here, if you want to write this next to the formula in your notes, please do. This formula exists to be used to find the displacement. So delta x is our displacement, delta x, delta d, it tells you how far you've traveled. You use this formula to find delta x when your acceleration is constant or when it's 0. In our earlier example, we were assuming acceleration was 0. You're moving at constant velocity, you're not accelerating. This formula works for that. So to read the formula out in full, delta x equals v, okay. This is v sub 0. Occasionally I'll call it v naught, and that's not, okay. My own notation is getting bothersome at this point. My apologies, everyone. One of the teachers here at the department is from South Africa, so he tends to use terms like this. And it means initial, it means 0. It means what was your velocity at time equals 0. This is the same as v initial. My brain uses them interchangeably, which is why I look at it and I don't see a problem when I'm writing my notes. My apologies. So this is v sub 0. All three of these, v initial, v 0, v naught, they all mean the same thing. Please write that down, because my own brain treats these as interchangeable. I'm probably going to write them in different ways, and I'm terribly sorry. So, an object's displacement will be equal to its initial velocity times time plus 1/2 times its acceleration times t squared. You can use this formula to figure out how far something is going to move over any period of time, as long as you know its initial velocity and its acceleration. So, to end us on very quickly, we're going to look at the second part of this question now. How far did that ball fall after those 3 seconds? Our original formula we used doesn't have a d in it. There's no displacement in this formula. We can't use this formula to figure out how far it fell. That's where this third formula comes in. We're going to use it once here. We're going to keep using it when we meet next time. to help get used to it for your homework. For right now, just at least expose you to it for the once. Change in displacement is equal to V initial times time is 1/2 times acceleration times time squared. We can use this specific formula to find how far you travel as you accelerate for some amount of time. Again, when you get in your car and you hit the gas, you don't stay still until you're at the speed you want to be at. You are moving as you speed up or slow down. You are moving some distance. And this formula tells you what that distance is. So, looking back at this question, we know we're in the air for 3 seconds. We know t. But what's our starting velocity? 0. We begin stationary, so this term is 0, which means this whole middle piece just goes away. A lot of times, pieces of this formula just fall out, which makes it convenient. That just leaves us with this. So, 1/2 times our acceleration, which is -9.8, times time squared. Our time is 3. Make sure you're only squaring the 3. Only square the 3. If it helps, just write it in as 9. You want to make sure you only square the 3 and you don't square the rest of it. Okay? But then you can plug in this into your calculator and you figure out how far you fall. I realize I crammed a strange new formula in at the end. We're going to revisit this next time, so you'll be good for it on your homework and on your labs and your quizzes and all that good stuff. If you have lab, remember we will be having lab this week, which means some of you are just going to come right back to this room in about 15 minutes. If you want to hang out around here, you can. If you want to go somewhere for a minute and come back, you can. If you have lab on Tuesday, go to the bathroom, get some water, get a snack if you need it. If you don't have lab today, I'll see you in lab later this week. Also come to lectures this week, and have an excellent week. Sorry, say again. So, on any other week, that might require you to come in at a different time, or I might be able to work out a virtual assignment for you if you're MIA for a week or two. But specifically for this week, our lab is just an algebra practice assignment, which I have here printed out. So I can just give you this, and as long as I have it by the end of the week, that's your lab assignment.
All right. So we just fill it as a lab thing?
That's it for today.
Thank you.
You're welcome.
So, will you just in person now, or can you do it right to our room?
I suppose it would be better if you didn't have to do it in this room. So you know what? Yeah, you can go ahead, you can take it later.
I'm gonna have to blow this up.
Sorry?
Do you have this like online? I can fill this out on my iPad with, then I can print it.